Ladies and gentlemen, distinguished professors and scientists, I'm very happy to have this opportunity to deliver an open ceremony speech at the Visual International Conference on Atom Purple Tomography and Microscopy 2022. On behalf of the Beijing University of Science and Technology, I would like to extend our warmest welcome to all the participants from different regions of the world for this visual APT&M 2022. This conference is the 59th International Field Emission Symposium, which is original dating back to 1952. Such a long history indicates that the International Field Emission Authority has successfully led these communities to fulfill its mission in promoting science and technology development of atom purple tomography. And the conference provides an important platform for scientists and researchers to exchange ideas and report their exciting research findings in high-field nanoscience and atom purple tomography. It is a great pleasure for NJUST to have this opportunity to host this important international event in Nanjing. It was 16 years ago that this international conference came to China for the first time, hosted by Sun Yat-sen University in 1906. At that time, only one 3D AP instrument produced by Oxford Nanoscience was installed at Shanghai University. 8 years later, Nanjing University of Science and Technology became the second university in China with a LEAP system installed. As a flagship instrument in the Center of Analytical Facilities at NJUST, APT in combination with the other advanced analytical techniques has greatly assisted research development at our university and fostered research cooperation with major research institutes, universities, and industries in China and overseas, and produced many publications in top journals, including Science and Nature. Today, there are 12 LEAP instruments installed in mainland China and Hong Kong. With these new instruments, APT will make significant contributions to science and technology development in China. I believe that it will not take such a long time for the conference back to China next time. We are experienced huge impacts of COVID-19 pandemic on our daily life. Research and international conferences confronting with such difficulties. This online international conference has attracted about 200 participants from different parts of the world. Germany, US, China, Australia, and the UK are top 5 countries with 19, 17, 14, 13, and 9% of participants in the APT&M 2022, respectively making this conference truly international. I hope that this online conference will mark the end of the COVID-19. A face-to-face conference will bring more freedom and better experience in communication and interactions. APT&M 2022 has offered many interesting topics covering fundamental physics, simulation, instrumentation, and advanced applications important for the APT technology development. Like invited talks and nearly 19 regular talks and over 20 posters address frontier research developments in APT technology and its applications. Enjoy fresh information released and new advanced debate in this research field, and be inspired by new technology and new ideas presented at the conference. With this opportunity, I wish a full success of APT&M 2022. Welcome you to visit Nanjing and Nanjing University of Science and Technology. Thank you for your attention.
Hi, good morning. Now I'm the Sure. My name is Gang Sha from Nanjing University of Technology. I will chair the first session about the technical section structural materials. There are 4 talks. The first one is the invited talk will be given by Professor Simon Ringer. The topic of his talk is towards atomic scale analytical tomography, why, what, and when. So first, I will just introduce Professor Simon Ringer. Professor Simon is my close friend. I have worked with him for over the last 7 years before I moved back to China. So Professor Simon Ringer is a material engineer specialized in relationship between microstructure of materials and their property and processing. His research is focused on the atomic scale design of microstructure, and his work spans the development of structural alloys, functional materials. His fundamental material science research has been translated into materials engineering via industry partnership in the area of advanced steel, aluminum alloy, and hard metals. Besides his own patents for materials engineering, his published research is cited extensively in the patent literature. His approach to materials science involves electron microscopy, atom probe microscopy, and computational materials simulation using density functional theory. He likes to think about the microstructure as a palette comprised of many attributes and length scale, from solid classing to green texturing. His main research contributions involve using the above approach to help achieve novel microstructure design and our methodological advance in microscopy. He has held appointments in Australia, Sweden, Japan, and the United States, and leads the establishment of a number of major research institutes and research facilities that now supports global academic and industrial engagement. He is professor of material science and engineering at the University of Sydney and serves as the university's academic director for core research facilities. In 2020, he was elected as the Australian Academy of Technology and Engineering. He is a fellow of International Office Emission Society. So let's give a speaker to Simon, and let's welcome his exciting invited talk. Okay, Simon, over to you.
Thank you. Fantastic. Well, thank you very much, Professor Shah, Gang. That was very gracious and all too long introduction. So thank you for that. And of course, I gotta share the screen. Thank you. Terrific.
Yes, that's good.
I will. Here we go.
So I think I have to move to the next speaker, and keep the program running. Thank you. So the next talk will be given by Levi Teig from the University of Sydney. The title of his talk about the characterization of a new ultra-wide field view atom probe microscope using model aluminum magnesium silicon alloy. Now, Teig, that's over to you. You can share your screen now.
Thanks a lot, Gang Sha. Thanks a lot for inviting me to having me in this presentation as well. I'm very grateful to be following Simon Ringer on the program. Big shoes to fill. Yes. So that's right. Good. I'm presenting today on a new ultra-wide field view atom probe microscope. Of course, by this I mean the new CAMICA in Viso. So the University of Sydney recently received the first CAMICA in Viso 6000 atom probe microscope, and it differs considerably from a LEAP in terms of its ion optics. So here's a basic schematic of the key elements. The first difference that should stand out to everybody is that the specimen passes through a counter electrode rather than being adjacent to a nearby local electrode. So one big difference one big consequence of this is that Inviso 6000 can only accept single tips, no half grids. Specimen is then irradiated by dual deep UV lasers, and due to the probably the significant difference between the specimen and the nearby electrodes, there's no voltage pulsing for this instrument. Ions then take approximately this path towards the detector. So those of you familiar with the LEAP, which I guess should be most people in the audience, will see this is quite different to this configuration is relatively different to the way a LEAP works. So as we received this brand new instrument, we knew that it was quite different to a LEAP. We went about characterizing the Inviso in several different ways using model systems. So today I'll be talking about a particular case study, Aluminium 6026, but throughout this presentation, there'll be several people from Sydney presenting on their studies of the Inviso. So let's kick on to what I've been looking at. So aluminium alloys, aluminium magnesium silicon alloys are routinely studied by Atom Probe. The particular alloy I was studying here was provided by some collaborators from MPIE Germany to look at the effect of deep cryogenic treatment on these nanoscale precipitates. But the reference heat treated sample is anyway ideal for study via Atom Probe because it's a relatively simple material. So I'll talk more about its microstructure and composition soon. But first I'll talk through the experiment which underpins this presentation. Before that, I'll talk about how the samples were prepared. So the alloy was sectioned into very conventional Atom Probe sample preparation procedure, sectioned into matchsticks, electrode polished using the universal solution, washed in methanol and stored in air. So nothing fancy there. So the experiment plan. The University of Sydney, prior to the Inviso, our latest generation Atom Probe was the LEAP 4000. So specimens of the aluminium alloy were loaded into the LEAP 4000 normally. Collected 20 million ions using laser pulsed Atom Probe with a 50 picojoules of energy. Warm it in the buffing chamber and then transfer it into our ferrovac vacuum and cryo transfer suitcase. Though in this experiment, we only used the vacuum part of that. Carry the ferrovac over to our Inviso and then vacuum transfer the SIP into the analysis chamber. Collect 150 million ions using laser pulsed Atom Probe with 400 picojoules of energy, and then reconstruct both data sets using IVAS. So if this is the first you've heard of the Inviso, it might seem like a rather complicated experiment just to know what this machine's all about. There was a reason we went to all this effort. This material is ideal for characterizing a new instrument because it's got a very simple mass spectrum with negligible overlap and almost nothing else. As you'll see, the microstructure is very beautiful when studied via Atom Probe. We know the geometry, we know the composition, more or less, and aluminium alloys run very well in Atom Probe. Why bother with the vacuum transfer? Because we can mainly maintain a pristine metal surface using the vacuum transfer. So whatever this exit surface was from the 4000 should be the starting surface in the 6000. Another advantage is that by not taking the tip out of a puck, we keep the orientation of the tip the same with respect to the detector to really try and minimize the differences between, the only difference should be the instrument in theory. And then all acquisition parameters were essentially default except laser pulse energy. And as I'll get to, we chose this based on the single plus, double plus charge state ratios. So now I'll walk through some of the running parameters from the LEAP 4000 and the Inviso to compare them. Some of you might find this interesting from actually running microscopes on your own. So 50 picojoule laser pulse, the LEAP 4000's voltage profile looks like this. There's then a large jump in running voltage when you transfer it to the Inviso, and then it runs really, really smoothly. When we first received the Inviso, we were surprised to learn that it runs at such high running voltages, but chips run really, really well at high voltages, and such a jump is actually normal and expected. It's pretty cool. So despite the large change in voltage, there's not a significant change in the aluminium plus double plus charge state ratio. So we can estimate the field using Kingham curves, and it all comes out at being kind of roughly the same. The charge state ratio is about 75, the field's about 18.5 to 19. Basically, the shorter laser wavelength, the dual lasers, the nominal laser pulse energy, about 8 times higher on the 6000 to what we'd use on our LEAP 4000. Mass spectrum. So we choose the first 20 million ions from each data set to ensure the signal to noise is equivalent. There are also actually some interesting differences in the mass spectrum between the two instruments. So at least for the aluminium alloys, I found that there's a lower background in the Inviso by far, almost an order of magnitude, but significantly more hydrogen in that 1 and 2 Dalton peaks. Not significant, doesn't appear to be significantly more hydrogen in the elsewhere in the mass spectrum, but certainly not so much 1 and 2 Dalton. Peak widths of the width half maximum I found to be relatively similar, but with longer tails, longer thermal tails, that is. But with a lower background, this may end up leading to greater chemical sensitivity. This alloy isn't really the best for studying that, though. Its composition is real. Nothing is particularly dilute in this alloy. So since the tip orientation was preserved through the transfer, the field of view can really be easily compared. So this shows the detector hit map of the LEAP 4000 with some important poles labeled. This shows the hit map for the Inviso 6000, and because it was the same orientation, we can actually just overlay them. So one thing that Kamika talked about with the Inviso is it has a significantly enhanced field of view, and I can definitely confirm that is true. Field of view of the Inviso 6000 is enormous. Illustrative here is probably these two poles, R11 and 202, are actually 90 degrees apart, and both are resolved or very nearly resolved in the detector space. Really cool. So these are reconstructed out of positions, but I don't think these really illustrate the effect of the field of view on the from the Inviso. So let me do a different type of visualization. So the blue dots show the aluminium position, and magnesium, so the purple surfaces are magnesium silicon iso surfaces. So this shows the reconstructed data from the LEAP 4000. And then, because the tip in the Inviso was essentially a direct continuation of that from the LEAP 4000, we can essentially just concatenate, line them up with the precipitates that are continuous in both, and see the enormous change in field of view between the two instruments. So just to quantify it, 35 to 60 nanometers in the LEAP 4000, that's the voltage increased. Moving it to 6000 instantly doubles the field of view to 120 and then expands to 160 by the end. The Inviso 6000 has an enormous field of view, and you see a very large number of precipitates very easily. Very, very cool. So there was, as I was hoping, there was actually one very lucky precipitate, which is present in both data sets. So you can see it there, which is exciting because it allows us to not only do chemistry over all of the precipitates, say on a proxygram of the iso surface, you can see there, but actually along an individual precipitate. And quite surprisingly, in this particular precipitate, there was actually a difference in chemistry. So in the LEAP 4000, it was a little bit poorer in the alloying elements, silicon and magnesium. I mean, these are 6000, it seems to be a little bit richer. It was exactly the same range file. Remember, the idea was to try and make these experiments as exactly the same as possible. Peak shapes are a little different in the Inviso. So the message of this slide is not the Inviso sees more alloying elements. The message of this slide is more care needs to be taken in ranging. You can't simply copy your workflows from the 4000 to the 6000. You need to work on them a little bit more. Still in the precipitates, there are some distortions at the edge of the data set and straight in the center. So a very quick analysis is just to look at all the precipitates in the file, draw lines over those in the core and the edge, and show that they're not exactly parallel. This particular precipitate is straight in the middle and bent at the edges, which is not what we expect from TEM studies of the material. The precipitates should be straight and not bent everywhere. We're not exactly sure why. Both Sydney and Kamika are looking into it and working on it. It's more of an issue when your precipitates are small, fine, and thin, like they are here. Perhaps it's related to the enormous field of view. We have distortions at the edge, but basically this is an open problem that we're looking at and working on. So again, on the mesh, the decelerating mesh is visible on the detector as high density regions. So this image shows a zoomed in part of the detector map. And you can kind of make out that there's a little bit more detail there than you'd expect. But it's also visible in the recon. So here we are. This is looking top down on the recons from before. Can't really see much at this scale, but as you zoom in, you can kind of see, hopefully over zoom you can see, there is sort of a grid pattern in the atomic size of the aluminium or the atomic sites of the aluminium here. So the simplest way to visualize this, I guess, is in the XY spatial distribution map, where the grid appears as these points, which are about, in my case, 1 millimeter nanometer away, 1 millimeter in detector space, 1 nanometer in recon space away from the origin. So it's not been me doing most of the studies on this. There's been others at the University of Sydney, but we expect this is going to be an issue for fine cluster analysis or short range ordering studies in the NVISO. And perhaps it can be overcome, but we're still looking into that too. So although the XY has the effect of the mesh, the information in Z is pretty much entirely unaffected. So this shows an SDM along the 022 pole in the Z direction. So looking down the pole, looking at the resolution in Z. The NVISO, if anything, has a more clear, although the full width half maximum is similar, we certainly have more peaks in the SDM to look at, which helps in reconstruction. In general, we've found the NVISO has pole patterns more commonly than we see on the LEAP, particularly for complicated materials. But Dr. Andrew Breen's presenting later today. I think he's got more of a discussion on resolution in the Atom Probe. So I'll look out for his talk. The last result I'll talk to is that there is an enormous increase in yields for the NVISO 6000. So the figure on the right shows good hits per run scraped from our Atom Probe databases for all of the 6026 that I've run. And there's a modest increase for the 6000 compared to 3000 voltage, but it's aluminium. It runs really, really well in voltage pulse mode. What we found is that the chips usually hit the voltage limit or the ion limit well and truly before they fracture. Chips basically don't fracture in the NVISO. It's really, really quite cool. So yield is more important for other LOS systems though, particularly where chips had a lot higher likelihood of fracture. So Siyu Huang is presenting tomorrow on zirconium alloys. He talks more about yield in the NVISO 6000. I'd urge you to see his talk to see what effect it's had on his work. So to wrap up, on the NVISO 6000, we found that when you have high sample yield, chips run, and greater field of view, recon is wide, you get enormous analysis volumes. And this is really exciting for when you had sparse precipitates or you wanted better counting statistics for chemistry, for geometry, for a lot of different things. And it means NVISO allows us to get difficult materials analyzed really quickly. Difficult materials usually run, and we see lots of them all at the same time. Fantastic stuff. But there are some challenges we still have with the NVISO. Distortions of the reconstruction edges an open problem that we and Kamiko, I think, are working on. The mesh contributes to that large field of view, but also leads to some interesting effects at the sort of the small clustering scale, and perhaps some changes to peak shapes and mass spectrum, but they need to be investigated a bit more. Either way, it's not another LEAP. It's a new type of instrument, and it requires new care and thought in analyzing data that comes off it. We're not quite done. There's more to do. So I ran in constant section mode. We can also run in constant field mode. It should be interesting to see how that changes in the NVISO. We can also have a closer look at that precipitate chemistry, look at different precipitates, look at many individual precipitates and see if there really is a change in chemistry, and correct the distortions as well. So that's it from me. Thanks for your time. If you have any questions, please let me know now. And of course, thanks to all of the people who contributed to this work, from ACMM, SMM, and the collaborators who provided the materials. Thank you.
Thank you, LabTech's exciting talk to share this new instruments information and also the comparison with the previous instrument like 4000. The results is really exciting. So I think everyone wants to get the hand on the new instrument now. Because we run out of time over time, so I think we will move to the next talks. And if anyone have questions, you can directly send an email to LabTech and to further discuss any issues you want to discuss. Okay, thanks, Larry. So let's move to the next talk. The next talk will be given by Sigland Nai from Jinan University. Her talk is about the accelerated evolution of hierarchical microstructure in iron silicon vanadium alloy. So now to speak to you, Sigland. So you can share your screen.
Okay, let me share my screen now.
You can put in play mode.
Yes, it's a little bit slow. Okay, should be fine now, I guess. Yeah. So, okay. Hi, everyone. My name is Sigla Nai from Jinan University or Nova Scientific in Guangzhou, China. I'm very happy for the opportunity to introduce our research on hierarchical microstructures, accelerated evolution of hierarchical microstructure in an iron silicon vanadium alloy. In this talk today, I will briefly introduce the concept of hierarchical microstructures and clarify some terminology, describe the material and experimental approach, and thereafter describe the material, present the result of the TEM and atom probe with a bit of a more detailed view on spatial distribution map analysis. I will also talk about the ratio of elastic and isotropy, the Zener ratio, and how we think it can be utilized to predict the behavior of hierarchical microstructures. Lastly, I will summarize our conclusion and hope for some interesting questions. Let me introduce the concept of hierarchical microstructures really quick. Hierarchical microstructures form when additional hierarchical particles are formed. They are typically observed in nickel, iron, or cobalt-based superalloys. Such hierarchical particles are interesting because they act as a strengthening mechanism. Since around 1961, such hierarchical particles have been observed in a variety of alloys, mainly in nickel-based alloys. These hierarchical particles can appear spherical or plates. Hierarchical microstructures change over time when exposed to high temperatures. And in general, we can observe two different pathways of metastability. Pathway 1 is continuous growth of a gamma particle and split of gamma prime. And pathway number 2 is growth and dissolution of gamma particles. This example of a nickel aluminum titanium alloy is following pathway 1. Spherical gamma particles emerge first in gamma prime precipitates and change their morphology into plates. The plates continue to grow and eventually split the gamma prime precipitates, which results in a loss of the strengthening effect you can see in the evolution of mechanical properties in the hardness curve on the right side here. The other example is a high entropy superalloy, also based on nickel, in which hierarchical microstructures follow pathway 2. Growth of spherical gamma particles followed by their dissolution, as shown in these 3 images at the bottom. In both cases, the presence of hierarchical microstructure is associated with improved strength, and that is why we are so interested in. With our research, we are trying to find ways to control the behavior of hierarchical microstructures and those nanoscale particles, enhancing their thermodynamic stabilities, to enable the development of new and stronger high temperature alloys. To understand how to tailor these properties of these hierarchical microstructures, we first need to understand the underlying mechanism and how they are related to phase chemistry and alloy composition. Research has already been done on hierarchical microstructures in FCC-based alloys, where in most cases, hierarchical particles first appears as spheres and then undergo a certain evolution. The material we study here is a iron silicon vanadium single crystal alloy with a BCC structure. In this alloy, additional particles appears as plates already after a very short aging time. Here we use TEM atom probe hardness measurement and thermal cal. The atom probe experiments were done in a straight flight path LEAP 5000 XS equipped with a UV laser. We use a laser pulse frequency of 833 kilohertz, a laser pulse energy of 0.8 nanojoule, and the sample we kept at 40 Kelvin during analysis. Our alloys microstructure looks a bit like a Egypt hieroglyphic writing. So let's take a look now at the iron silicon vanadium hieroglyphic hierarchical phase separation. This iron silicon vanadium alloy shows a two-phase structure after initial aging, where ordered alpha 1 precipitates, here in white, are embedded in a solid solution alpha matrix shown dark. When this material is further aged at 873 Kelvin, a maze-like hierarchical microstructure appears, and the additional hierarchical plates are also alpha phase. During aging, they continuously grow and eventually split the alpha-1 precipitate, which means that this alloy follows metastability pathway 1. The alloy shows the highest hardness after 24 hours of aging, which is marked by a red box here. To get an idea of the general distribution of alloying elements, we perform TEM EDS analysis. Here, we focus on a smaller area showing some alpha matrix, alpha-1 precipitates with alpha plates inside. We measured the concentration along 2 lines across all phases from X0 to X1 and from Y0 to Y1. The profile clearly reveals that the alpha matrix and plate phases contains more iron than alpha-1 phase, and that in turn, the alpha-1 precipitate phase contains more silicon and vanadium. The HAADF image and the element mappings on the right side shows this trend very clear. So the tendency is clear, but we need atom probe for a detailed quantification of these small structures. Okay, now let's take a look at our atom probe data, this time of a sample age for 6 hours only. In the 3D reconstruction, we can now clearly see how the alpha plates are interconnected, forming a 3D maze-like structure. The interface are visualized with a 81 atomic percent iron isosurface, the proxygram between alpha-1 precipitate and alpha matrix, and between the alpha-1 precipitate and hierarchical alpha particles look identical. The alpha matrix and hierarchical particles have the same composition. After 24 hours of aging, the hierarchical alpha plates became much larger. This data set only contains alpha-1 precipitate phase with hierarchical alpha plates inside, also visualized using the 81 atomic percent iron isosurface. The proxygram analysis looks almost identical to that from the previous slide. We place a small cylinder perpendicular to the interface to extract a 1D concentration profile shown here at the bottom. The 1D profile basically reproduced the information from the proxygram nicely, showing the changing composition of each phase with no changes to composition observed. We conclude that phase equilibrium is achieved. We took all the phases compositions from atom probe and plot them in a ternary phase diagram of iron, silicon, vanadium at 873 Kelvin. The nominal composition is shown as gray dots. The red lines show the phase boundary between the alpha and alpha-1 phase field at 1073 Kelvin. Our atom probe data points for the sample age at about 1073 Kelvin for 3 hours lie exactly on this line. Atom probe data points from samples aged at 873 Kelvin all lie on the related phase boundaries, even after 6 hours, the shortest time we age the sample for. This clearly illustrates that equilibrium phase composition are achieved after short aging times. Using the compositional data from alpha-1 phase, we calculate the entropy of mixing, H-mix. While the ordered alpha-1 phase tries to get rid of extra iron, the iron is continuously pushed into an alpha plate. This process lowers the entropy of mixing about 3 kilojoules per mole after 768 hours of aging at 873 Kelvin. We also took a closer look at the inside of an alpha-1 precipitate phase and found lattice planes close to a 001 pole, with the alpha-1 phase having a lattice parameter of 0.56 nanometer. We expect to see a pure iron or a very iron-rich plane every 0.28 nanometer, as shown in the model of this alpha-1 unit cell here on the right side. The same observation, but with a 0.14 nanometer offset should be made for the silicon and vanadium planes. However, in our data, here we can make no clear distinction between an alpha and beta gamma planes. This could be a co-evaporation effect resulting from the different evaporation fields and the relatively high laser pulse energy we use. For the same small volume with the lattice planes, we perform a spatial distribution map analysis as expected. For a AA pair, we see iron interatomic distance with a periodicity of 0.28 nanometers, indicating that iron only occupies cornicite. Silicon shows the same periodicity, which we believe that originates from silicon only occupying body center sites. Vanadium shows a variety of interatomic distance and seems to be offset ever so slightly from silicon. This could hint at vanadium occupying both corner and center positions. The spatial distribution map on the right side for an AB pair shows additional peak at 0.14 nanometer steps for iron vanadium and for silicon vanadium, indicating again that vanadium may occupy corner and body center positions. In contrast to our expectations, however, iron silicon does not clearly show a peak for 0.14 nanometer steps. This could be due to an evaporation artifact. To confirm if our experimentation makes sense, we are currently working on creating simulated iron probe data for this ordered alpha 1 structure, on which one we can run a spatial distribution map analysis on and compare that to our experimental data. Now let's switch gears and look into morphological stability of these hierarchical particles. Our iron-based alloy here shows a super fast evolution of hierarchical particles. Alpha plates are already observed after only 6 hours of aging. Other alloys such as nickel aluminum titanium alloy initially shows gamma spheres and plates only appear after 24 hours of aging. The nickel silicon iron alloy mentioned earlier shows gamma spheres and those remaining spherical up to 384 hours of aging. We took a close look at a variety of such hierarchical alloys and their properties. Initially, we thought that the lattice misfit might be a direct indicator of how hierarchical particles would behave. However, the iron silicon vanadium alloy and the nickel silicon iron alloy have almost the same negative lattice misfit, but the evolution of hierarchical particles could not be more different. Of course, the iron silicon vanadium alloy has a BCC structure and the nickel silicon iron a FCC structure, which needs to be considered too. We categorize the morphological evolution of hierarchical particles in 3 different ways according to these 3 different alloys. First, early formation of plates. Second, morphological transformation from spheres to plates. 3, stable spherical morphology. Comparing that to the Zener ratio of each face, which is the ratio of elastic and isotropy, we conclude certain pairings of Zener ratio will favor a particular morphological evolution of hierarchical particles. If the Zener ratio of the host face is smaller than that of the hierarchical particle face, their morphology will be plate-like, even in a very early stage of aging. If the Zener ratio of the host face is similar to or equal that of the hierarchical particle face, the morphology will initially be spherical and eventually transfer into plate. If the Zener ratio of the host face is larger than that of the hierarchical particle face, their morphology will be spherical and stable over long aging time. Let's conclude this talk briefly. We saw hierarchical phase separation of alpha 1 precipitates with formation of alpha plates. Peak hardness is 570 HV after 873 Kelvin 24 hours with hierarchical microstructure. The alloy follows metastability pathway 1. Alpha plates grow fast and split alpha 1 precipitates. Atom probe phase composition match predicted phase equilibria. Formation mechanism of alpha plates akin to previously studied alloys. Supersaturation of ordered precipitates revealed through hierarchical phase separation. Spatial distribution map analysis are not 100% conclusive. We propose the Zener ratio as metric for morphological stability of hierarchical particles. Phase-targeted alloying strategies could specifically tailor properties of hierarchical particles. And thank you very much for your attention and time.
Okay, I would like to thank speakers for a very interesting talk. And the microstructure you presented is amazing. It looks like Egypt characters. Also,
Yeah.
the mechanism revealed is exciting. Yes, that's great. So because the time it seems like we have to move on. So if anyone have questions, just go to the chat and to talk with Celinda and about his research. Okay, so let's move to the next one. The next talk will be given by Dr. Renmin Niu from the University of Sydney. The title of his talk is Director of the Observation for Hydrogen Atoms at the Cementite Ferrite Interface. Now, yes, it's over to you. Hi, Celinda, can you close your screen share?
Well, I can't share.
Yeah. 他这个怎么给他 close？ 他的 screen share。他现在 close 了吗 ？Yes, Celinda, can you leave this? Yes, close your screen share. The bottom. Share screen. Yes, can you close that one? Okay. Good. So now.
Oh, okay.
Yes.
Now
Okay.
I'm able to share.
That's your turn. Okay, that's great. Thank you.
Right. Hi, everybody. Good morning, good afternoon, and good evening to everyone in the world. My name is Renmin Niu, and I'm a postdoctoral research fellow from the University of Sydney. So back to 2008, I was an undergraduate student in the Beijing University of Science and Technology. So because of the pandemic issue, I couldn't be back to my mother university, but it's such a shame, but I'm really honored that I'm invited to give the presentation here. So the topic today is hydrogen-enhanced deformation in perlite. So this is a research project that's empowered by the correlated micromechanical testing and cryo-atom probe tomography. So hydrogen embrittlement is quite classic research or engineering topic that basically describes the mechanical degradation that when materials exposing to hydrogen environment. As you can see from the typical uniaxial tensile tests here, the left sample, which is undergo hydrogen charging, shows much reduced ductility and significant reduction in fracture toughness, and showing brittle fracture instead of normally behaved ductile fracture behavior and making things. So because of hydrogen embrittlement, it's making the mechanical property of the materials very unpredictable, and which is very crucial to engineering, is a big problem, especially to the pipeline networks. And especially considering the future endeavor when people want to transport hydrogen in those pipeline networks. So we don't want these catastrophes to happen. So what we can do about it? From material science perspective, we would find a reason from the microstructures of materials. If we do look into the literature, we see the most commonly seen microstructures in pipeline steels are ferrite, which is the face, and the perlite, a microstructure constructed with lamella, ferrite, and the cementite faces. So these faces are interesting because in the literature we found that this microstructure is exactly where crack initiates after hydrogen charging when material affected by hydrogen. Okay, so as you can see to the left, of those images, SEM images showing the fractalography of a hydrogen embrittled steel after tensile tests and is failed. Those cracks or crack embryos were found just at in the perlite microstructure and mostly between the ferrite cementite interface. And these cracks sometimes propagate transversing the lamella, sometimes parallel to the lamella, is not quite clearly determined. So and explained. So how hydrogen affect the deformation of a pearlite is a question. And this is a gap we would like to fill. So the key problem to this project is how hydrogen affect the deformation of a pearlite, and why is that? So to tackle with this problem, we designed the project into 3 sections. So the first one will characterize uncharged ferrite cementite interface. Look into the microstructure, look into the mechanical property, and also use atom probe tomography to investigate the chemical composition of this phase, of this interface. And section 2 will be about using the similar type of characterization techniques, but more advanced type of it, to investigate where hydrogen is in this interface, and how hydrogen is affecting on the mechanical behavior of this interface. And the third section will be a simulation part, which rationalize our results captured in previously. So my talk will not focus on the FTE part, and we'll come to our very talented PhD student Pang Yu Liu's session tomorrow. He's our brilliant DFT guy. So the method we used is mostly micromechanical testing and atom probe tomography. Micromechanical testing is a method that you can do mechanical testing inside the SEM or TEM with small sized materials with dimensions ranging from a few hundred nanometers to a few microns. You got the mechanical response and you got the stress strain response at simultaneously with the maximum resolution capability of a electron microscope. Atom probe, of course, it doesn't need to introduce more in this community, but what we used is the deuterium charging and the cryo transfer technique. So you can charge the atom probe tips with electrochemical methods and quench it in liquid nitrogen, transfer with this high cryo vacuum suitcase directly to the analysis stage and characterize where hydrogen is in the tip. So based on these 2 techniques, we finally can get a correlation between the mechanical effects of hydrogen and the location of hydrogen in the microstructure. So here is the data. For uncharged, undeformed pearlite, this is the original structure of a hypoeutactoid steel. The lamella structure here you see is pearlite, while this one is ferrite. And if we take some TEM images, you see the lamella structure right over there. And based on high resolution, atomic resolution, Harvey stem, and also electron diffraction patterns, you'll recognize this interface between cementite and the ferrite. It's semi-coherent. It has a certain orientation relationship, what people call isochive orientation relationship. And we really using the location of these atoms to perform geometry analysis, you can observe there's lattice strain towards to this interface that ultimately leading to an elastic strain in the cementite of compression near the interface and the ferrite expanding near the interface. So, and in terms of chemical composition, we perform atom probe tomography. I electropolish a tip and then annihilate it with FIB technique to finally locate a cementite layer just on top of the tip and run the standard atom probe tomography experiment with voltage mode. And we observe this 1D concentration profile across the interface. And you'll see that value is a little bit lower than the expected one. Of course, this quantification of carbon is a long history issue in the atom probe APT community, that we look into the literature and really overestimate the carbon by assigning C4 to 24 Dalton. So this one, we assign it totally to C4 to get it still under the estimated value. And the reconstruction is done by using those poles. So next is about the mechanical property of this interface. So we prepare pillars in this orientation. So all the pillars we have are prepared with 110 grains with the help of VDSD. And then we prepare the pillars into the diameter is one micron, and we place those lamella just inclined almost 40 to 50 degrees to trigger interfacial slip. And you can see during the deformation, these interfaces are slipped, and this is exactly how it looks inside SEM. Right. You can see the slip propagates along the interface, and those intermittency is called strain bursts, which reflects the collective dislocation behaviors in the slip plane. And after the compression test, we further slice this into a cross section and check the postmortem TEM images. As you can see here, the interface is really slipped, and the slip is exactly happened at the interface. After that, we characterize the hydrogen charge perlite. So we do the hydrogen charging on a bulk piece of perlite, and then prepare the pillar on top of this bulk piece for perlite. This bulk piece is charged, and it serves, because of the bulky nature of it, it serves like a hydrogen reservoir. So after hydrogen charging, we conduct a similar type of in-situ compression test, and here is the result. So based on the stress strain curves, we show a significant reduction of the strengths, and based on the morphology of the stress strain curves, we see the strain burst behavior is less significant, meaning that reflecting or implying that the dislocation are undergo less barriers for their motion. So to double check with the results, we performed thermal distortion spectroscopy to simulate the in-situ compression experiment after hydrogen charging. The black dots here are exactly the black square here are uncharged perlite, and the blue ones are hydrogen charged for 30 minutes and then released in vacuum for 30 minutes, which is the earliest time, the quickest experiment we can do. And even though after we did the experiment very slow, and after we set up the in-situ experiment and the sample was rested in the SEM for around 4 hours, there are still significant amount of hydrogen left in the sample, which implies that the mechanical property difference we observed are due to the hydrogen in the material. We also repeated the experiment to show that this result is repeatable. And we cut the cross-section of the hydrogen charged pillar, compressed pillar, and when we check the interface, surprisingly, we see that the slip are no longer exactly at the interface. And why is that? So we try to see where hydrogen is in the charged perlite sample. So this is a hydrogen atom probe tomography with cryocharging and the transfer technique, with hydrogen charging and cryotransfer technique. And you see the black one here represents carbon, the red ones represents deuterium, and so this is a cementite phase. And if we plot this on the concentration, you will find that actually deuterium is depleted at the interface instead of what people usually believe segregates to it. And we also believe that this depletion is the reason for that slip offset to the interface. And to repeat the experiment, we have another data to show that the deuterium depletion at the interface. So with these two information here, first one is that we observe their elastic strain towards to the boundary, phase boundary. And the second variable is that we can sort of get the existence of carbon vacancy in our cementate, because even we overestimate the carbon value is still less than expected. So we reasonably expect that carbon vacancy will be in there in the cementate, and also some other literature shows the same similar conclusions. So based on these two variables, we do we do several DFT calculations to calculate the hydrogen potential energy. And the background color here represents the strain value. And when it's towards to the interface, this strain is getting higher. And also this strain will lead to an energy landscape that's changing between two interfaces. So, and we also account for the existence of carbon vacancy. If it's without carbon vacancy, the hydrogen potential energy will be higher. If there is carbon vacancy, this energy will be much lower, and introduce a significant discrepancy between these two interfaces. This results ultimately leading to the results, our ATOM probe observations that hydrogen is trapped into cementite and absorbed to cementite as when creating a depletion layer in the ferrite phase next to the ferrite cementite phase boundary. Okay, so here is the conclusions. Significant softening effect of hydrogen, especially to the region containing cementite interface, was found. And hydrogen trapping in perlite occurs in the ferrite cementite bulk, not as much as we believe at the cementite ferrite interface. That's it. Thank you.
Thank Dr. Niel's exciting talk about share your information about hydrogen distributions in this cementite ferrite interface. It is very exciting results. Again, and anyone may ask one question quickly, so because we will have a session break, so we can accommodate one question. Yes. Hi. Okay. Yes. Yeah, Jun, you can ask questions.
Okay. Okay.
And,
okay.
Yeah.
Thank you for your presentation. And I have a question about the TDS analysis.
TDS analysis.
Yeah. The total trapped hydrogen is so small. Because this axis, PBB mass, and however your observation by ATOM probe, hydrogen concentration is so high. Why?
Yes. Okay, so this TDS study is to confirm the existence of hydrogen in our in situ sample. This is not the exact situation for atom probe, cryo atom probe experiment. So we expect that the concentration of hydrogen in atom probe which will be much higher than this.
Yeah. And okay,
yes,
but
yes.
Maybe you show the 0.5 atomic percent in ferrite by atom probe, observed by atom probe. Okay, so this still, it means the ferrite still have a lot of ability of trapping so many hydrogen. But your TDS analysis shows a very small hydrogen trapping.
Oh, sorry.
So
this
the difference, okay.
Sorry. This TDS is conducted with this bulk sample, Well, in situ charging
sample, it's okay. Yeah. Yes. Okay.
Yes, but in situ charging, we conduct with the we conduct the charging on the tips. In this situation. So we charge the tips with 2.2 volts for around 30 seconds. And we believe this charging condition oversaturated hydrogen in the ether probe tips. Yes, that's why we observe a very high concentration in the atom probe data.
Okay, and in previous paper, the in perlite, hydrogen trapping amount is so small before the deformation. Okay, now, but your atom probe data shows so many hydrogen in ferrite. Okay, so and I don't know the difference between the TDA. So this is so about a 1 atomic percent in ferrite.
Yes, that's a lot. Yes,
and
that's a lot.
It's so strange. Okay, and discuss later. Okay, maybe no time.
I guess maybe it's also related to the cryo transfer process. This time our experiment was doing unexpectedly smooth. A tip didn't fail, it didn't fracture, and everything runs perfectly. So probably because of the cryo transfer process that we luckily succeed in this experiment.
And we have to consider there are some artifacts. Okay.
Yes.
Okay.
I think it's a very interesting question. It's also very interesting topic. I think you can discuss it later. And now we have about 6 minutes break. So we will come back like 9:50. Okay. So have a break and Simon will chair the next session. Thank you all for this morning's exciting talk.
Hello, everyone. And yeah, thanks for tuning in. So I'm actually over in the US at the moment. So yeah, it's been a busy day at another conference here. But yeah, really wanted to join the meeting and just give you my take on some of the initial data that we're collecting off our exciting new atom probe, the Kamika Inviso 6000. And yeah, I'll be following on from some of the nice work that Levi was showing earlier. So yeah, I'll quickly go through some of the new capabilities and some of the changes on the new platform, and then go into a bit of a performance characterization with a few different material case studies. So in particular, I'm interested in looking at additively manufactured, or more specifically electron powder bed fusion produced Haynes 282, which is a nickel-based superalloy. So we'll be looking at that a little bit, and then just doing a bit of a semi-quantitative and more of a qualitative look at some of these performance metrics. And you know, obviously, as we're going to collect more and more data on this new instrument, we'll be able to look into that into a bit more detail. But hopefully, you'll get a bit of a sense of the data that we're collecting off the instrument so far, and then we'll just do a quick discussion of some of the challenges and next steps that we're intending to do. So yeah, we're very excited to receive the Inviso 6000 on the 17th of February earlier this year. And so, you know, we started out doing a number of different test runs on that, and just running a whole bunch of different types of materials of interest that we're looking at in the various research groups at the University of Sydney. So obviously one of the main technological improvements with this new platform is the dual beam deep UV laser pulsing. So we have a shorter wavelength there compared to the previous LEAP platforms. And yeah, this is basically enabling a significantly higher specimen yield, a higher mass resolving power in general, and this dual beam capability where the laser beam split and illuminates the specimen from either side, allows for a more symmetric tip evaporation, and that has some implications for simplifying sort of reconstruction protocols and the like, and also enabling faster detection rates, so we can crank up that detection rate a little bit more with this new laser technology. And the other big advancement here, of course, is the larger field of view, which is enabled through new ion optics with the double Einstein lens and a new counter electrode concept. So this also contributes to the faster detection rates, because whereas before with the leaps, you're losing quite a lot of the ions and they weren't getting through the electrode. Now we're capturing a lot more of the tip, and potentially the entire tip surface if you tip sharp enough. And yeah, so for the same equivalent evaporation rate, you're getting a much faster detection rate. But we can't run multi-tip specimens with this new configuration, so you have to actually insert your atom probe specimen through the orifice of the counter electrode. And so because of that, we need to sort of change up a few of the protocols around particularly fib-based specimen preparation. Can't look at multi-tip arrays and then grid type specimens. There's some other nice features that are new additions to our lab. So we've got the automatic specimen carousel, which was available on the 5000 series, but yeah, we don't have that in our lab. So that's a nice addition for us. We've got a cryo suitcase stock to the buffer chamber. So that's quite nice. We also had one on our 4000 XSI that was into the buffer, into the load lock. So now into the buffer chamber. So that's good. And there's some good software improvements as well when you're running the experiment. So some on-the-fly automatic ranging capability and on-the-fly automatic reconstruction, which for the most part seems to be working quite well. But yeah, a few challenges that we're sort of trying to mitigate and work through with the no multi-tip specimens, and yeah, we're trying to work through some reconstruction calibration questions and also some practical implications for handling large data sets. So, you know, these large data sets we're getting are awesome, of course, but yeah, how are we going to curate those, store those, visualize those, you know, with maybe we're going to need to get increasing computational power to do that as we're going from, you know, data sets in the tens of millions of atoms up in well into the hundreds of millions of atoms pretty routinely into the billions. So that's something to consider. So yeah, myself and others at the University of Sydney have just been running a whole bunch of different materials, and I just sort of provided a little bit of a snapshot of the kinds of things that we're sort of looking into. So of course we're doing quite a few tests on pure aluminium, not so interesting from a material science point of view potentially, but you know, that provides us a really good test case to develop reconstruction protocols and the like on. We wanted to see how it ran on some semiconductor materials, so we're running some dope silicon experiments. Meng Wei is going to give a talk, I think, after me. He's interested in high entropy alloys and running a few of that. Yeah, you saw Levi's talk on the aluminum alloy, and I've been doing some of my things, experiments mainly on Haynes 282. And yeah, just getting a sense of the information you're getting off the detector space there. Of course, it's very dependent as well on the parameters which you run the experiment, not just the instrument. But in general, we're seeing quite good crystallographic information. Yeah, you know, more so than probably what we were seeing on the other instruments. In my case, for Haynes 282, maybe not so much, but that may just be to do with optimization of the conditions there. So, of course, yeah, we've got the nice wider angular field of view, and maybe not such as elegant experiment as Levi performed on the same tip specimen, but you know, if you compare a sort of a typical experiment run on the 4000 XSI and the voltage pulsing mode, you might get a detector map looking something like this, and you can overlay a stereographic projection or projection of that crystal structure and calculate it's about a 50-degree angular field of view in this case. You can get a little bit further out there and maybe up to 60, but on the Invisio, you're really getting out to around 80 or 90 degrees angular field of view. And so that's very nice, capturing a lot more of the material, the microstructure there, and also potentially capturing the whole tip if your tip's sharp enough, I believe. And so that has some interesting implications as well, particularly if you're looking at, you know, it would be very interesting for looking at sort of oxidation, surface reactions, coatings, and things like that. I think the Invisio is going to be really great for that kind of thing. So just a few quick notes on in-depth spatial resolution. I mean, it's looking pretty good. We weren't really expecting it to be particularly like better than the previous platforms, but we wanted to check that we were getting a reasonable good spatial resolution, and at least in depth, it looks quite good, at least comparable to what we're getting on the LEAP instruments when you're getting these crystallographic features within your detector map. So I've just done a Z or 1D spatial distribution map corresponding reconstructed region here. So we're histogramming the interatomic distance, and you can quite easily pick up the lattice planes there. So that's looking reasonably good in that sense. I just wanted to give a quick little overview of this electron powder bed fusion produced Haynes 282, which I'm interested in. So this is part of a larger study that we're working on in Simon Ringer's group there. It's part of an OSMURI project where we're looking into the structure, property, and processing relationships of additively manufactured materials, in particular metals. And so this was built on a RCAM Q10 from GE and under a random scan strategy. And just to give you a bit of background here, and the regions of interest, that we've been looking at different regions of interest, but what I'm showing today are sort of coming from the top region here. And just some notes on specimen yield. So it's actually a little bit difficult to quantify because it's dependent on the experimental parameters, of course, and the tip condition. And also because the Inviso 6000 in general is just so high that we generally stop the experiments before they fracture. So, I mean, I guess that's the take-home message there, and from a practical point of view, that it's looking really good. So, these Haynes 282 specimens, they're already running reasonably well on our leaps. We're getting into the tens of millions of atoms fairly regularly, even when we're running it. We're particularly interested in crystallographic information, so those are run at cold temperature and voltage pulsing. But yeah, on the Inviso, definitely easily, routinely getting into the hundreds of millions. The longest tip ran for over 500 million atoms, although I didn't run one experiment. I split that into two. But yeah, that's all looking very good from that point of view. And of course, that means larger data sets. So whereas on LEAP platforms, you'd be happy with several tens of millions of atoms. Now we're getting hundreds of millions of atoms. We're also able to run at a faster detection rate, partly because of the larger field of view. So for the same equivalent sort of evaporation, sort of stress on the tip, you can run at a high detection rate, but you can also crank that up a little bit higher due to the new laser technology there. And yeah, so we can get a significantly faster acquisition. And what's maybe interesting to note here is, at least on these sort of length scales for the gamma prime precipitates that we see here in the LEAP, you're often going to get those precipitates being cut off. They're not just going to fit into the whole volume, whereas here you've got a much better chance of encapsulating a precipitate of this length scale within the reconstruction, which is nice. And just some notes on the mass resolving power. Again, I haven't done a big longitudinal study here yet, but just comparing the mass spectrum between these two data sets, we can see that we get significantly higher mass resolving power, really high full width half maximum measured off the main nickel peak here. And yeah, and this is in general seeing sharper peaks, and I'm also in general seeing lower noise floors, similar to what Levi was showing. But I am also observing higher hydrogen signal, hydrogen peaks, the 1 and 2 Dalton. And so we're still investigating as to sort of why that might be the case, and if we can sort of mitigate that, because obviously we're particularly Julie Canny's group's interested in looking at hydrogen in metals, and yeah, we want to try and sort of avoid all that hydrogen background. So I thought I'd just quickly sort of jump into a little bit of work that I'm doing on detector mapping. I'm particularly interested in the crystallographic information, and yeah, we can basically filter the detector maps on the atom probe to potentially enhance the crystallographic information. And I don't have time to go into all these methods today, but yeah, this helps us index the crystal and helps us with the reconstruction calibration and the like. And yeah, trying to do similar things on the Inviso. So this was actually an experiment run in voltage pulsing mode. So the vast majority of experiments will be doing laser pulsing, but we do have voltage pulsing capability. But I was observing sort of a strange sort of aberration, and we're still a bit unsure as to why that might be happening, whether that was a problem with the electrode or, but yeah, sort of others were sort of observing that. So, but at least for the voltage pulsing, we're getting comparable crystallographic information to what we were observing in the LEAPs. This was running at a little bit of a higher temperature as well, to the side that I showed before. The laser pulsing, I don't see so much crystallographic information, at least for the cases that well, the experimental conditions that I've been looking at, but it might again be a case of just optimizing those, of sort of cycling between 100 and 800 picojoule laser energies. This was just an example from 400, but there is still some crystallographic information that we're collecting there, which we could use to study like potentially site occupancy information, the gamma prime, and also help with calibration. But yeah, recon calibration is a bit more challenging in the Inviso because we're going out to those larger fields of view. I think the ways in which we go about calculating image compression factor need to be reviewed. It might not be so yeah, it might not sort of work so well for the Inviso. So if you sort of go through and try and work out an image compression factor on this test aluminium data set here, it's quite small at the center, but quite large out towards the periphery. So a better model for ion projections on the detector for the Inviso is needed, and that's something we're working on and discussing with Kamika. And part of that is going from a sort of a pseudo stereo projection to an equidistant azimuthal projection, which there was—
That's 3 minutes, Andrew.
Yeah, so paper that put out there a number of years ago. So we want to sort of apply those equidistant azimuthal projections to the Inviso, see if that gives us a better modeling of the projections, but also there might be some other corrections that are going to need to be put in. So at the moment, yeah, basically having a bit of trouble trying to crystallographically calibrate these reconstructions, but the default reconstruction parameters seem to be giving us a reasonable reconstruction. But yeah, as Levi pointed out, there is some distortions out towards the periphery of the tip, which we're going to need to correct with better reconstruction protocols. And then also this Einsel lens is really awesome for giving us the larger field of view, but we are actually seeing this come through on the detector map and then also into the reconstruction. And there's questions over what's that doing to the fine interatomic relationships there. And so, yeah, just in summary, Inviso offers some really exciting opportunities with the larger field of view and large data sets and the mass resolving power, but we've still got some challenges we're working through on reconstruction and yeah, and the like. And I'd just like to acknowledge some of the following people that contributed here with discussions, and just finishing on a happy note that just recently my wife and I welcomed first child into the world. So yeah, Emma was born about a couple of months ago. And so yeah, we're very excited about that. But yeah, it's been a busy time. So thank you very much for listening.
Thank you, Andrew. Yes, and yeah, congrats, baby Emma. How wonderful. So yeah, no, thank you for that overview of where things seem to be on things Inviso. Yeah, questions for Andrew Breen. Andrew, the question of the compression factor and the variation across the face there.
Yeah.
Just give people a sense of the order of magnitude effects here. So if something goes from 2.44 to 4.48, that seems like a big number. What is that doing to us?
Well, for our standard reconstruction protocol that we're doing on AP Suite and IVAS, and we typically just use a constant image compression factor across the reconstruction. And for the LEAP data, where we have a smaller field of view, that has been served us reasonably well and has worked. But I think now, but as Bad had pointed out a few years ago and things, the projection model that we're using is not quite right. It should be closer to equidistant azimuthal, but maybe with this new configuration of ion optics, it's different still. So I think we need to come up with new reconstruction protocols, really. Yeah, so we're getting distortions out to the periphery at the moment that we're going to need to correct, but I'm confident that we can correct for those if we understand this. Yeah, the compression factors better.
Thank you. Okay, gone in terms of questions for Andrew Breen. Andrew,
yes, I have questions.
Go ahead.
Why the resolution is improved so significantly compared to the LEAP 3000s? Is it due to the flat path?
The in-depth, yeah, the in-depth spatial resolution seems very good, but we still need to look into the lateral resolution. So we can do that using 2D spatial distribution maps. At the moment, we're a little bit concerned about what this grid might be doing to that, but there has been some preliminary things that I've seen where we can actually still pick up some lattice information laterally.
Andrew, I think the question was around the mass resolution.
The mass resolution.
Oh, okay. Yes. Why is it so much better?
Mm-hmm.
It's just to do with the new laser energy, I think, mainly. So this deep UV wavelength. Sorry, yeah, wavelength. Which is, yeah, giving significantly higher, in general, mass resolution, we're seeing.
different lasing regime. Okay, well, thank you. I think we'll wind it up there. There's probably many more things to talk about in how to wrangle in Viso in the way we would ultimately like. Going to be talking about reconstruction. Dennis, over to you.
Thank you, Simon. Hope everyone can hear me and see my screen. So
looks
today,
good, and you a 3-minute warning.
Okay, thanks. So today I will be talking about the work we'll be doing for the reconstruction of some of our minerals. We like our rocks, and we like to also develop some methods to improve how we can look at these minerals. So I'd like to acknowledge the funding from the Australian Research Council for this research, and also all my co-workers. If I can change the slide. Okay, so Atom Probe in geosciences, we've seen the applications of this tool to our field really surging in recent years. And we can thank the development of the UV laser for this increase in the different applications that we could target with the tool. Our mass spectrum can be quite complicated sometimes. There's an illustration here of a monazite, which is a rare earth phosphate, with many molecules forming during analysis, and then sometimes quite complex and large molecules. As you can see also on the, sorry, I'm trying to find my laser pointer. On the detector image here, we rarely see crystallographic planes in our data to help us with the reconstructions. So because of these two reasons, we don't really see any lattice planes in our data sets unless there are some pure alloys or some alloys or some metals, natural metals. So really, that makes our life a little bit complicated when we try to think about reconstruction parameters that we should use for reconstructing our data sets. So that was the drive to maybe determine a solution to this problem by having some rapid but also relatively accurate reconstructions for minerals. So what can we do in this case? So one good way to do it, obviously, is by doing some electron microscopy of the APT tips, and using the tip profile reconstruction mode in IVAS or AP Suite, we can then determine quite accurately the shape of our reconstruction. However, we know that electron microscopy can cause some issues. Surface oxidation, hydrocarbon contamination are two important ones, and these basically increase our chance of failure rate. So increases our rate of failure. And this is really nicely illustrated in this study by Habig and Kummer, that could image the contamination layer and the effect it has on the data quality, and this including noisy data and also microfractures. So we basically want to avoid this strategy of having some intense electron imaging of our tips on all of our tips, in order to increase our chance to get good data. So if we think about the voltage reconstruction evolution modes reconstruction, in that case we don't need to know prior to the reconstruction the exact shape of our specimen, and there are variables in the equation which are basically the detector efficiency, and that we know relatively well depending on which instrument we use. There's also the atomic volume, and that is mineral specific. We can calculate that, so that's easy. Then we have the image compression factor, Xi, where as I say, we don't have the crystallographic planes to actually measure it from our data. So, but something we don't really have an idea of. Is also the K factor, which can sometimes vary, and finally the electric fields, which should be material specific. The thing we know though is that the main parameters which influence the image compression factor and the K factor are the specimen geometry, but also the large scale instrument chamber geometry. So in other words, the specimen electrode and detector distance. It is thought that these variations can be limited between specimens of the same shape if the field absorption image fills up the detector consistently between experiments. And this will basically ensure a reproducible specimen to electrode to detector geometry. And I must thank that for this statement in one of his paper, because if we take care of doing this exercise of matching the field absorption image consistently between our different specimens, then we can maybe assume constant K and Xi constants, which will mean that only the electric field will vary between different experiments, which then makes the equation much more achievable to resolve. So what we've done is the approach we've taken with some success is to overlay images of atom probe specimens before and after analysis. So analyzing it for some time and then overlaying the two images to measure with as much accuracy as possible the distance, of length of the material we have removed during the analysis. I must say that in order to have a nice tip shape to start with, we have first put the specimen in the atom probe, run them for a few million atoms to make sure that we have a stable evaporation and hemispherical tip shape, and then we can do our accurate imaging and do that exercise. Following the analysis, we can reconstruct the data. Then we can, sort of test different, iteratively test some field values and see what works and gives us some good results. Some sort of a coarse approach to start with, and then we can later refine. So to do our imaging, we started by using our APT&M, which is an FEI talus, and we use
Dennis, I think we've lost the audio there on your side. So, hey, Dennis, we can't. Dennis, are you hearing? We've got an audio issue, I think. Unfortunately, you just suddenly dropped out, or quite spontaneously. That's a bummer. Can't hear anything, I'm so sorry to say. Could be a thought to just jump out and come back in. That might be one way to hack it.
Can you hear me now?
Ah, yes, we can hear you. You're back.
Yeah, I must apologize. Sometimes my Zoom is playing some tricks on me, and I have to do a couple of tricks to get it back online. So I apologize about that.
No worries.
So I was saying basically on this slide that we used the TM at Curtin, which is a FEI Talus, and the grid holder and the tungsten grids from Sydney. The issue with that process was that we had to take the grids out to put it in our TM holder. And in that process, we lost and damaged too many tips. So this was not a really good way to do it at the large scale. What we've done then is we just used an SEM. So this is a Tuscan Clara when we have at Curtin, one of the latest generation, which provided some really good results. In there, we used a pre-tilted specimen holder in order to get the atom probe specimen normal to the beam. But once we overlay the images, we can do it for several tips, and when we ran for several different durations of between 40 million, between 7 to 40 million ions. Then we can, with the different iterative field value, we can see what is the value which matches the best the measured length between the reconstructed length. And after we have made these iterative values, we can further refine these values by making small adjustments so that we have a perfect one-to-one average line between the reconstructed and the measured length. So we had some good results, and this is an example here of a lead cluster in zircon. If we use the default value from zirconium, which is an electric field of 28 volt per nanometer, we see when we have some distortion and probably an elongated cluster in the Z direction. If we use the parameters we actually measured, we see when the cluster is round and probably closer to what we expect. At this stage, that's when Dennis goes a little bit stupid, because I tried to do this for a few minerals, 12 in total. And this slide just to illustrate, that was quite a large body of work where we did this process for many different minerals to try to estimate as best as we could the reconstruction parameters. These are summarized into a manuscript which is published in last year's APT&M special issue in M&M. And if you go and check out this paper, you'll see that there is a statement here which says that if you chase out the DOI number, you may find new parameters. And if you chase it, you'll find this page which hosts the data sets. And at the bottom here, you'll see when there's a version 2. If you click on this, you'll find when there's an extra 2 parameters that you'll find for sphalerite, but also corundum. And
3 minutes, Dennis.
Thank you. This is basically also to invite everyone in the community to use these values, to maybe update them as they wish, but also if they want to participate to this effort and give values for some minerals they've been working on, or some other materials when they think could be benefiting from this approach. Don't hesitate to get in touch with me, and we can upload supporting figures and values to your work. That's all I was going to say today. Sorry again about the problems with the sounds.
Not at all. Not at all. That was great. Thank you very much, Dennis. Super. So Dennis's paper is open for questions. And Dennis, while we're waiting for a question, I wonder, was there any of these minerals that were more or less amenable to the specimen length approach? And if that's true, why would that be?
So they all work pretty well with this approach. I had some issues with things like appetite, for example. You see, then there is no uncertainties for this mineral because it was very difficult to image them back and forth and before and after analysis. I think the electron beam sometimes damaged the minerals too badly that once we put them back into the atom probe to have a long run, they'll basically fracture. So some minerals were very tricky like this. I tried others like iron oxide, such as gutite, which is the hydrated iron oxide. Couldn't get it to work either. So there is a limitation here, and the minerals need to be resistant to electron beam microscopy, basically.
Thank you. There's a comment, I think, from Baptiste in the chat there around quoting a single field value. So you might, I don't know if you want to have a quick look at that, Dennis, and a quick comment. Otherwise, you can take it up.
Yeah, so that's a problem when we encountered and we thought about only moderately. It is true that the field value will change in data sets, and that was apparent especially in oxides. No, in silicate, I can't remember which ones, but if you measure the radius of the specimens at the end of the analysis, you'll see then the field value, then you can calculate from this based on the voltage, and is very different from the one we calculate from the specimen length approach. So yes, it is apparent when the field value changes with the voltage basically and the radius. But the way we like to think about it is that we do this.
Well, what do you know? The sound has come in and disappeared again. And Dennis, what we'll do is we'll leave it there. So I'm going to thank you very much because we've lost a few minutes as we go along. Very interesting, and of course, there's an opportunity to continue the dialogue in the chat or in other ways, of course. So thank you for that. We're going to go to our last three talks for this session. These are three talks from the United States. And we begin with the presentation from Nasiha Cardwell. And Nasiha, hope you're on Kamika in the United States. Rob, over to you.
All right, great.
I'll give you a 3-minute warning as well.
Great. Can you hear me?
Looks good and sounds good.
All right, great. So in this presentation, we'll take a quick look at the software used in atom probe tomography. And we'll see how software can make your life better and how your life can actually get better maybe for free. So with that, we'll move into it. On the way to quantitative data analysis, we actually cross a lot of different software boundaries. From specimen preparation, data acquisition, these take a significant amount of time and the time to knowledge race. So making the software in this part of the process as user-friendly as possible and as automated as much as possible will free up more time to focus on data analysis. So we'll briefly go through what some of those automation processes are, and then we'll get to looking at the analysis software, which is actually the microscope. Meaning the analysis software is what fits the standard definition of the microscope. It's what makes the enlarged image of an object. So that makes atom probe different from other microscopies. So we're all familiar with the traditional atom probe workflow, and software is included in every step. Typically, an operator will spend a good fraction of the day making specimens on a focused ion beam instrument, for example. These to be transferred to the atom probe. And depending on how long the measurements take, you might take data from a few samples or maybe a few dozen in a day, with lots of hands-on time for testing electrodes, focusing on laser, navigating to the desired microchips. And then during the initial data acquisition, getting through the initial apex material, maybe some oxide or gallium, perhaps evaporating off the active cap, and then you set your laser power and detection rate for one or more regions of interest once you've gotten to that portion of the specimen. The data then would, of course, be manually reconstructed and analyzed. With automation, we've made some strides in this process from specimen preparation all the way through reconstruction. With the automation, for example, introduced by Thermo Fisher Scientific, a great deal of preparation work can be automated, not necessarily speeding up the process, but freeing the user to do other more important tasks. After the samples are transferred into the Atom probe, the data can be acquired and reconstructed automatically with CONICA's latest automation features, including automated electrode testing, automated focused laser, chain acquisition to run multiple samples unattended, and scripted acquisition, where the Atom probe actually monitors the composition or noise level and can make changes to the run conditions unattended without the operator being there. So in addition to that, as the data are being collected, the reconstructions can be completely automated. So one can just stop by later in the day and start doing the real work, the data analysis that you do with your software microscope. So how much time savings are actually realized with these different pieces of automation? I've got an example here of an operator maybe preparing and analyzing six specimens during the day. And there's different steps in the process, with blue steps indicating a manual process or something that you have to be hands-on, and green indicating an automated or unattended process. Some of these having some crossover. Without automation, we have nearly all the time requiring hands-on engagement with instruments. So the total acquisition time would be variable depending on the specimen, but one might expect having to spend as much as 10 hours ushering your specimens through the process to final data analysis. With automation added to the specimen preparation, data acquisition, and reconstruction, we can see that although there's not a huge total time savings, this process still might take all day, but much less of it needs to be hands-on, freeing up as much as half your time to do other more valuable tasks. Of course, you need to have access to that analysis software, and so we can see what the options are. There's actually some really simple ways to share data and visualize the data. As simple as there's a 3D viewer built into Windows now. It's built by a presentation mode. You can see that you can actually export .gov files for AP Suite and embed these right into native Office applications or other software like Active Office applications. So really, when we do that, there's also things like browsers, so you can have isosurface or sample data turned on and off. But of course, these are really just qualitative ways to look at the data. These things are useful to pass a message, but they're not doing quantitative analysis. And so, as many of you know, IBIS, which is used for doing this quantitative analysis, is about 20 years old, and it relies upon libraries that are not necessarily being updated and supported anymore. And at some point in time, IBIS just won't be compatible with the latest Windows versions. So, therefore, we built AP Suite, Atom Probe Suite, not just as a replacement, of course. AP Suite brings in a lot of new capabilities. If you haven't moved to AP Suite yet from IBIS 3.8, it's definitely time to do so. There's a growing number of features that are not available on IBIS 3.8, and included some really nice things with the integrated database architecture, being able to integrate fig images, plots for experiments right in the database itself. The ability to do spatial ranging is very exciting. So based on an isosurface, for example, you can define regions that have different range files. So the classic one is going from nickel silicide into silicon. If you have a single range file, you're going to have nickel showing up everywhere in your data set, because even though if you get into nearly pure silicon, those ranges still exist. A 1D profile, for example, will have errors in it based on ranging. So we can have now different subregions defined by ROIs or isosurfaces, subgroups that can have different range files. There's new region of interest selection tools, the ability to undo and redo changes when you move a region of interest. And there's lots more stuff. And I'm not going to go through all these different features. There's a lot of nice new features, and even more will be available in just a couple of months with the next AP Suite update. We're also excited to introduce a much more integrated third-party software support. So the next presentation will give an overview of those capabilities, and that suite of tools that come with an integrated database. So we have now a standalone version that's going to be released in the next couple of months that doesn't include that functionality. And this will act much more like the traditional IBIS 3.8. We'll have a simple and quick installation, but we'll still have all the data analysis power and new features that are in the fully integrated database AP Suite version. So you'll have everything in it except the control software and the database. And so really will look and feel much like people use IBIS 3.8 right now. So these features can be more fully understood by going to atompro.com and enrolling in our Thinkific training platform. It's free and it includes a great deal of information in the first steps of installing the software, includes how to operate the AtomPro, goes through basic reconstruction and maybe advanced data analysis functions. So if you've not signed up, I challenge you to see what's available in the Thinkific platform. And I challenge you to tell me you didn't learn something new, because there's lots of information there, and I'm sure you'll come across things that will be new to you and remind you some different ways to approach problems. Also, of course, there's an integrated software manual in AP Suite and IBIS. If you haven't opened up that software manual, I guarantee there's also new stuff for you there. Of course, we recognize that not everybody has direct access to your own AtomPro, and you don't have direct access to the analysis software that comes with that. And so we've heard from many of our most active system owners that access to software is a serious problem, slowing down research, slowing down solving material science problems. And so to address this, we've come up with a few solutions over the years. Of course, we have our IBIS Lite program. If you don't know about that, it's go to atompro.com and find that. It's been very successful with perhaps 1,000 free licenses being distributed, a few thousand free licenses being distributed on every continent all around the world. So this has been a very popular program. You get a free version of the IBIS software that has some limitations to it. So for example, as successful as the program is, IBIS Lite does have some limitations, and these limitations weren't accidental. They were put in place for very specific reasons. We envisioned IBIS Lite being used by a visiting scientist to finish manuscript images or like images and charts and plots. And these visiting scientists might not have been familiar with the intricacies of APT reconstruction. We also knew that IBIS Lite would be installed on computer systems with much less power, probably lower minimum requirements for properly working software. But over the years, the APT community and the world has changed. The community has grown and has grown more familiar with reconstruction and the challenges of AtomPro tomography. And additionally, the power of computers available have made nearly every computer built able to do more powerful calculations and keep more information in memory. So in effect, the landscape and the environment that visiting scientists had has evolved over time. And so our often software must evolve too. So starting last month, we decided to make a new program, very much like the IBIS Lite program. It's a no-cost license, but this program offers the full power of AP Suite, including reconstruction, cluster analysis, decomposition. It's really a full powerful license of our latest and greatest software. So who's eligible for this type of program? To be eligible, you need to be a research scientist employed or affiliated with an academic institution or a government research laboratory. And you need to be doing research that's public access, so it can't be for a private company or for profit. In collaboration, or you also need to be in collaboration with a participating AtomPro group from a different institution. So that means members of existing groups that have their own software that came with the installation system aren't eligible for this program. Additionally, to participate in this group, you need to be collaborating. Participating in this program, you need to be collaborating with an AtomPro group that has a system under full warranty or a full service coverage contract. And this is to make sure that if you're getting data, it's going to be high quality data and the system is working properly. There's a lot more details about this program. I encourage you to check them out if you're interested at atompro.com. Just like IBIS Lite, you apply online. It is a little bit different that you get a digital license, not a physical license. And so we'll send you a digital fee that will be specific to the computer that you are going to use with. So only one computer for one license. And in response to us sharing this software for free, we ask that if you use this program to create presentations or create a manuscript, you share that information with us, send us a PDF of the data presentation that you present, if it's a public presentation, or if you are fortunate enough to get a manuscript published. And so that's our way of trying to keep the finger on the pulse of what is the latest research that's being done. And that can help guide us, our software.
3 minutes, Rob.
Over the time. Yep, I'm right there. Thank you. So these instructions on how to apply for this program, who's eligible, are being sent to APT sites worldwide. And the standalone license that I mentioned will be available in just a couple of months is included in this program. And so we're really excited. We've seen the community asking for these things, and we have delivered, we hope. I always enjoy thanking my team coworkers. We've been working together doing this for 20 years, and I'm really proud of the work that we've done and happy to be able to enable more people to have access to the power of atom probe tomography with a free software microscope. Thank you.
Terrific. Thank you very much, Rob. Very good. Well, paper is open for questions and comments. I mean, I wonder if you want to comment here, Rob, and please, folks, sing out if you've got a question. I can't see all of the hands up necessarily. So it's a no-cost offering.
That's right.
I noticed you mentioned that you've got to be, participating groups have to be paying full service agreements. So, you know, there is actually a cost, isn't there?
Well, it's not the cost to the collaborator. So the visiting scientists that's visiting, you know, I think some of our classic national laboratories that have a large user base that comes through on a traveling basis. You know, the feedback was really strong that these are good scientists. They know atom probe, but they don't have access to the software, and there's a limited number of licenses. So it's really, you know, slowing down the work out there. So this is a response specifically to those use cases, but I think there's lots of use cases, different institutions around the world.
Got it. Thank you. Well, thank you for sharing that, Rob, and great to have the QR code there and the other details, and folks can follow that up in their own time. I thank you once again. And we will move along to our final presentation for this session. This is a presentation from James Payne, also of the United States, and also to talk about the AP Suite extension infrastructure. So James, if you're ready to roll.
I am.
Let's do it. Thank you. And I will also give you a 3-minute warning towards the end. Rob needs to stop sharing.
Can you stop sharing?
I got to stop sharing. Sorry, I'm having trouble with my window hid.
Great, thank you.
Right. All right. All right, greetings, everyone. My name is Jim Payne. I'm a software engineer at Kamika, and today I'm really glad to have the opportunity to discuss, as Rob alluded to, one of the exciting new features in the upcoming version of AP Suite that's scheduled to be released hopefully by the end of the year. AP Suite will be receiving some core infrastructure updates and some new features that are going to help facilitate users to write custom software extensions that can be loaded in AP Suite. So what does this mean for you? So at the core, these extensions are just software packages that are loaded into AP Suite, and this can be used to modify AP Suite's existing functionality in certain ways. But it's a really powerful tool that advanced users can even use to even add entirely new analysis features of their own design. There's some work involved, and so we don't want it would undermine the work involved in creating one of these if it was hard to share and load these into AP Suite. So a core design requirement was that users could easily discover and load your custom analysis into their version of AP Suite. This can help facilitate sharing with colleagues or, if you wish, with the broader community. And you can do this by following our standard distribution method that we've laid out as the method of packaging and sharing these extensions. Upon launch, we're also going to be, Kamika will be providing an online catalog of some initial extensions to get you started. This serves to demonstrate some of the power of what you can do with these extensions. And to assist the development of new extensions, we are publishing all of the source code for these on our Kamika's GitHub page. And these can be used for references to help you get started quickly and reference guides to demonstrate how you can leverage this to your own purposes. So I want to quickly just touch upon what this looks like in the next version of AP Suite. We're going to look at the new extension management feature that's found under the configuration section of AP Suite if you're using it, which I encourage you to do so. The Browse tab here will show the list of extensions that are available from Kamika's hosted online catalog. When you select one of these, you get a list of extra details on the right side, the name, author, current version, so that they can be updated independently of AP Suite, and a brief description of what it will do. And then you can, from here, simply click install, update, or uninstall to apply this extension to your instance of AP Suite. And that's it for a user. It should be very straightforward and simple for an average user to take the extension that you've created and start working with it in your own application. So while adding them in an application is pretty simple, developing one takes a little bit more effort. So I'd like to talk over what that process will look like and what are some of the capabilities that it will enable. The flexibility of this infrastructure does demand that the developer of the extension must have at least a baseline programming understanding. The extensions are developed outside of AP Suite using Microsoft Visual Studio or an equivalent. And the main structure is developed in C#, as that's what AP Suite is developed in. But because of the very low-level basic implementation, we have the opportunity to build compatibility layers on top of this so that we can in the future support other languages such as Python or whatever the community really demands. So to help simplify development, we are also going to be working on creating some public templates that can be used to quickly create a new extension by just filling in some basic information, as you can see, like name and description, and it will scaffold most of the code for you. So you can focus on immediately focusing on just taking your data and analyzing the way you want. These templates and some quick start guides will be found on our GitHub site, which I'll also have a link to at the end. So once the developer has created this project, the actual substance of these extensions comes from new application programming interfaces that are what allows the extension to interact with AP Suite. These APIs are just contracts that define what you can ask AP Suite to do and what AP Suite can work with in your extension. But by separating this out of AP Suite, we can apply some meaningful versioning to it that you can build against. And this gives us necessary tools to support backwards compatibility. The main feature here is that updates to AP Suite and minor versions of the API won't break your extension that you've worked hard on developing unless there are some major overhaul, which then you may have to update for. We really don't want to break your extension with every minor release of AP Suite. Upon release, we are focusing on one initial API target, and that's providing superior access to analyzing your data. This implementation totally replaces the existing, much more limited custom analysis support that we had in our current AP Suite versions. But because of the very low-level implementation of the extensions, we can build upon this foundation in new ways to expand this extensibility of AP Suite into other parts of the application. In the future, we're going to be targeting improving access to customization of the reconstruction process itself. But for now, because what's coming out in the near future will focus on writing custom analysis, let's take a look at what that provides you. This API allows broad access to many new aspects of the analysis tree workspace in AP Suite. Most importantly, it exposes direct access to the raw reconstructed data and provides methods of filtering it as you want. It supports creating custom graphic user interfaces to represent your analysis or integrating with our own 3D chart. The comprehensive list of functionality is frankly too long to fully cover here. So I'd like to touch on a couple of examples and talk about how they use some of the new custom analysis features. And hopefully they can give you some idea of how you can use it yourself to take your analysis to the next level. So these are mostly contrived examples that don't really serve any purpose. So I'm just going to walk you through what they're doing. This first example demonstrates an ability to create custom data filters. And this one's really exciting to me. This basically allows you to take your raw data with position, mass charge, instrument data, possibly, and using that to filter your ions on a per ion basis. This allows you to select exactly what you want to select and frees you from limitations of only selecting data from a spatial region. This filter is fully integrated with our existing analysis tree hierarchy. So in this example, I've created a custom filter that filters out a subset of ions, and I've applied it to clusters. So you can see the white dots I've added, the white highlight I've added selects, in this case, half of the ions in these clusters. Again, a contrived example. But this ability to select individual ions can also be combined with other aspects of our custom analysis API that can even allow you to ask AP Suite to try to return or recalculate some experimental data if you have the original files. This can help you access the raw instrument data in some cases, or calculated data such as hit multiplicity, which can then be used in further analysis. By combining all these resources, these code-based data filters really allow AP Suite to achieve an unprecedented level of precise data selection for further analysis. It's important to note that after you've created one of these, you can apply any of our other analyses or your own further custom analyses on top of that filtered data. And here's just a brief example of how I've created one underneath a isosurface and some of the example of code of how this filter works at a pretty low level. This next example, I won't linger on too much, but I'd like to just demonstrate that the ability to create any graphic user interface for your to return the results of your custom analysis. This is intended to be a bit more of an advanced feature, and our templates may help you get started, but this would maybe take a little more effort, or you could contact Kamika for help in getting started if you wanted to take this route. By creating your own custom analysis, your own graphic interface, you can use a lot of AP Suite's own existing charts, 2D, 3D charts, histograms, tables. You can also use standard UI controls, or you can actually access third-party charting libraries. In this case, I've grabbed another free library for charting a pie chart. If you have other tools that you'd like to represent, it's likely that you can pull them in and render them directly in AP Suite. You can also render static images. So if some of our tools are not able to represent your data interactively, you can render it as an image and display the image in AP Suite to consolidate all of your analysis. And our final analysis I'd like to talk about a little is one of the most exciting to me. I think this has some of the most useful potential. We understand that many users of AP Suite are not developers that are not familiar with C#, and this will obviously limit the accessibility of this functionality. However, you may often have experience with working with other common data analysis tools, for example, commonly Python. So this final example is a proof of concept that we hope to release in the near future for use that will allow the data from AP Suite to be piped into a Python interpreter and run a custom Python script of your own selection, and then return the data back into AP Suite for further processing or visualization. In this case, I've taken the reconstructed data, run it to this run function, and as you can see, it returns the data into an AP Suite window just to demonstrate the bidirectionality of this extension. This is not ready and ready for immediate use, but we are currently working on fleshing it out. And this is really exciting to me because I think it will we can write an entire compatibility layer between the extensions and Python, which will allow you to quickly bring any Python scripts you might have and integrate them directly into AP Suite. This can allow you to, right, and this, thank you. And this can allow you to then use your own tools, languages and tools of choice, or perhaps call other programs on your software to filter your data, return it back to AP Suite, and then further run our analyses or on the data that you return. So these examples have really just scratched the surface of what this infrastructure allows. It really is very flexible and gives us a broad base of support to help build new tools to support you in using AP Suite in your own way. I'd like to take a moment to just acknowledge the efforts of our software and applications team members who also help bring this functionality to you. So thank you. And when you would like to get started creating your first app extensions, when you receive AP Suite 6.3, please go to our company's GitHub page at Kamika APT, github.com/KamikaAPT. And you'll be directed to quick start guides and resources to get you started. And we look forward to see what you can develop and share with these tools. Thank you very much. Any questions?
Nice. Thank you very much, Jim. Thank you. Yeah, so Jim's presentation is open for questions. Jim, to your last slide there about the interlayer to C#. I mean, you talked about that coming down the pipe. I mean, we teach our students in Python everything, you know, pretty much in science is done in Python. I mean, our undergrads don't even hardly know what MATLAB was anymore because everything's in Python. I'm kind of curious about the C# decision, but when is this interlayer, as you describe it, going to be working? I mean, is it a 2023 thing or further out than that?
This interaction layer doesn't require any further development of AP Suite itself. Basically, it just builds a layer, for you to write against that can then be used in our in AP Suite. What this means is that we're focusing right now on actually getting the AP Suite version properly ready, and then from there we can push this layer out after that. And it is one of our highest priorities. So I can't give you an exact timeline, but I would say hopefully with 2023, early 2023.
Thank you.
I don't want to make any commitments there. That's
understood. Understood. Very good. Rightio. Well, thank you for that, Jim. Lots of developments going on. Good to see. And I think at this point, I'll hand back to you, gang, and thank all of our speakers for their presentations in this session.
Okay, I would like to thank all you all to give a very nice presentation this morning, and it's very exciting. So the afternoon session will continue over later. So make sure everyone come to the conference on time, and we need to control the talk time within the time limits, so we will not run our time. Thank you very much for your joining. So see you later this afternoon. Okay, bye-bye.